So this video will start chapter 7 and go over section 7.1 and 7.2. Chapter 7 is on the three states of matter: gases, liquids, and solids, and intermolecular attractive forces. So we'll go through section 7.1, which is a review of the three states of matter. On the left, we have the solid state here illustrated. So the properties of the solid states are a definite volume. You cannot compress or expand the volume of a solid. The solids maintain their shape. It keeps their shape. And the reason why it's like that, it's because solid particles lie close together in a regular pattern. So at the molecular or atomic level, it looks like the picture on the left, where all the green balls are packed together and you see a pattern. It's organized, ordered. And so they are held very strongly together, and that's why the solid keeps its shape and has a definite volume. In the liquid state, we also have a definite volume, but the liquid will take the shape of the container. So the liquids can flow compared to solids. And if we compare the atomic illustration, the liquid particles are close together again, but they can move past one another. So they can move around and rotate. And so then it's not ordered anymore. You can see that it's packed, but there is no pattern. It's not organized. It's random. And so there is less forces holding the particles together, and so they can roll around and move, you know, from one area and slide into another area. And so that explains the properties of liquid. Then in the gas state, there is no definite volume for a gas. And so the gas will assume the volume of its container. So the more volume you provide to a gas, the more it will expand into that volume. So you can compress a gas into a smaller volume. And if you compress a gas into a cylindrical tank, then it will take that shape. But if you compress it into a balloon, it will take the shape of the balloon. So gases take the shape of the container. And that's because at the atomic level, the gas particles are very far apart from each other, and they move around constantly. So they fly around in straight lines until they hit a wall and then bounce and fly in another direction. So existing as a gas, liquid, or solid depends on the balance between two things: the kinetic energy of the particles and the strength of the interactions between the particles. So that's what, you know, the balance between these two things will determine if you have a solid, a gas, or a liquid at room temperature. And so let's go over this using this table that summarizes the properties of liquid, gases, and solid. Here it reminds you about the property of shape and volume and the arrangement of particles, which we covered already. So then there is the density, and see how density of gases is very low. You have very few atoms and so mass per unit of volume. The density of liquids and solids are both considered high, but solids are even more dense than liquids. And so if you have a solid, liquid, or gas at room temperature will depend on the balance between the kinetic energy of the particles. And the kinetic of energy represents the energy of movement of the particles. And so the more the particles move, the higher the average kinetic energy for that substance. And so for a gas in particular, gases have a very high kinetic energy. And so their molecules are moving very fast. And that's why they're far apart from each other, because they fly around. But if you look at a solid, the movement of the particle is slow. So, and it's even, you know, only vibrating around a fixed position. So you have to imagine those atoms that we saw packed together. They're vibrating, but they're staying in their ordered, you know, lattice or network. So they move around that fixed position. So that's why solids keep their shape. And so that slow movement, it means they have a low kinetic energy, right? Kinetic energy is energy of movement. And now if we compare that with the interactions between the particles, so there are some attractions that exist between particles, and they can be non-existent, like in gases, because, you know, the particles fly around. There's nothing that, you know, attract them next to each other. And so there's no interactions in the gas state. And then in the liquid state, there is some interactions, and that's why molecules are packed together. But the interactions allow the liquid's particle to still flow and roll and slide past one another, which is not possible anymore in the solid state, because the interactions are very strong between the particles in the solid state. And so that's why you have a solid when you have a strong intermolecular attractive forces and low kinetic energy. So these two properties of average kinetic energy and strength of interactions, you know, there is a balance between the two, and that determines if you have a gas, a liquid, or a solid at room temperature for a given substance. So section 7.2 is on gases and pressure. So this chapter will go over gases first. So the properties of gases are explained by what we call the kinetic molecular theory of gases. So scientists have come up with this theory that explains what are gases. So a gas consists of particles that move randomly and rapidly. So you see in the illustration to the right here that the particles are, the arrow here symbolizes the movement. And so they fly around in all kinds of directions. There is no overall directions. They each move at the, you know, in their own direction. And when they hit the wall of a container, they bounce and fly back in another direction. So you also notice that the size of the gas particle is small compared to the space between the particles, right? The particles are the pink spheres, and there is all that empty space between them, right? So there's a lot of room between the particles of gas. Gas particles exert no attractive forces on each other, right? There is nothing that attract them to, you know, to each other. There's neither any repulsive forces that repel them from each other. So no interactive or no intermolecular forces between the gas particles. The kinetic energy of the gas particles increases with increasing temperature. So gases have a high average kinetic energy. That's what gives them the strength to, you know, or the, you know, the energy to move around. And when you increase the temperature, that energy increases even more, and so they will fly and speed up even more, right? So temperature is telling you that particles will move even faster if temperature increases. When gas particles collide with each other, they rebound and travel in new directions. So a bit like billiard balls, when they hit the edge of the table, they bounce and move in a new direction, right? So gas particles do that with the walls of the container they are in. And so this kinetic molecular theory explains the gas's properties very well, and that's why it's still holding as the true model for gases. Because the theory explains the properties of shape and volume, the fact that you can expand the volume, that the gases will fill the container they are in because they fly until they hit a wall. It explains that they are randomly arranged. There's no order. Particles are also very far apart from each other. There's a lot of empty space between them. And because of that, density is low because you have very little mass in a given amount of volume. So their densities are not usually given in grams per milliliter, which is the unit used for densities of solids and liquids. For gases, it's typically in grams per liter, right? We need a larger volume to have a more comparable mass. So grams per liter is usually the unit for the density of gases. The kinetic molecular theory explains that particles of gases are moving very fast, and that there is no interactions between the particles. So when we talk about a gas, we need to tell about its pressure, the property of pressure. Because when gases, particles collide with the wall of a container, they exert a pressure. Imagine a particle hitting a wall. Where it hits the wall, it's like pushing on it, right? And so that is called a force. And you can, give a value to a force per unit area. And that's what pressure is about. Pressure, the symbol capital P, is a force, symbol capital F, exerted per unit area, represented by capital A. And so pressure is a force per unit area. And imagine that you have a lot of particles hitting a wall at the same time and with a high speed. If temperature is high, then pressure will be higher, right? There will be more pushes on the wall in this case. And so the units of pressures are numerous. These are only a few, the most common ones. The main one is the atmosphere. Atmosphere is a unit of pressure. And, at sea level, typically the pressure of the atmosphere, the layer of gas that surrounds the planet Earth, this exerts a pressure of 1 atmosphere, and the symbol is ATM. And so 1 atmosphere is equal to 760 millimeters of mercury. Remember how Hg is the symbol for mercury. That's also equal to 760 torr. Torr is a unit that comes from Italian scientist Torricelli, who actually found out about the millimeters of mercury. 1 atmosphere is also equal to 14.7 psi. So psi is pound per square inches. Pound per square inches really shows you how pressure is a force per unit area, because the force is represented in pound, and per square inch tells you, the unit area. And then it's also expressed in Pascal. Pressure can be in Pascal, and 1 atmosphere is equal to 101,325 Pascal. So PA is the symbol for Pascal. Pascal is the unit used in the international system of measures of units. So all of these units are, as they are written here, are equal to each other, right? 760 millimeters of mercury is equal to 760 torr, which is also equal to 14.7 psi, which is also equal to 101,325 Pascal, which are all equal to 1 atmosphere, right? You can write all kinds of equality statements from these. So tire pressure is measured in pound per square inches. So maybe you've seen that in your car, if you have one. If you open the door, inside the door, it says the PSI that the tires need for a car. Atmospheric pressure based on altitude is usually measured in kilopascal. Kilo is the prefix kilo in front of Pascal. Atmospheric pressure in a lab is usually measured in millimeters of mercury. So millimeters, Hg for mercury, or in atmosphere, ATM. So that's why we have all these different units, because depending on the situations, the unit that was used was different. So let's learn how to convert units of pressure, and we will use this exercise for that. The atmospheric pressure in Seattle is measured at 0.982 atmosphere. What is the pressure in units of millimeters of mercury, kilopascal, and psi? And you're given the equality between atmosphere and millimeters of mercury, and between millimeters of mercury and psi, psi and atmosphere, and pascals and psi, and you need to understand that all these equal signs apply to all the statements in those equal signs, okay? So please practice this on your own before you watch the answer. So let's do first the conversion of 0.982 atmosphere into millimeters of mercury. So for this, we will need the equality that converts millimeters of mercury to atmosphere, and it's the one that is written here as the first equality. 1 atmosphere equals 760 millimeters of mercury. So because the given amount here is in atmosphere, right? The 0.982 atmosphere is your given amount. You will want to use the conversion factor such that the atmospheres are cancelled. So the 1 atmosphere will be on the bottom of the conversion factor, and the 760 millimeters of mercury will be on top. So you see that atmosphere cancel this way. And in the calculator, you do 0.892 times 760, and that's 746.32 millimeters of mercury, right? The unit left is millimeters of mercury. So you see how 760 has a dot, which signals that the 0 is significant. So we have 3 sig figs in 760. The 1 atmosphere is exact, and 0.982 atmosphere has 3 sig figs. So we will keep 3 sig figs at the end, and that's why we keep the 746 millimeters of mercury. Let's change that to kilo. No, well, no, let's do PSI first. So we start with the same given amount, 0.982 atmosphere, and this time we want to change that to PSI. And so you want the equality to say 1 atmosphere equals 14.7 PSI, and you will want the 1 atmosphere in the denominator of the conversion factor and the PSI on top, so that the atmosphere cancel and we're left with PSI, which is the unit we want. Atmosphere cancel, we're left with PSI. In the calculator, you do 0.982 times 14.7. The calculator answer is 14.4354. So same as earlier, we need to keep 3 sig figs, and so it's going to be 14.4. That's the third sig fig. What comes after the 4 is a 3, so we run down and we just keep the 4 and drop everything after that. Let's now change that into kilopascal. And so the equality here we have is between atmosphere and pascals. So we will need to first change the atmospheres into pascals and then the pascals into kilopascal. And so again, the given amount is in atmosphere. So we'll want the 1 atmosphere in the denominator of the first conversion factor and the 325 Pascal on top. The second conversion factor will change the pascals into kilopascals, and the relationship is that 1 kilopascal is equal to 1,000 Pascal, right? Kilo is the prefix with the value of 1,000. So if you change kilo by 1,000, you get this equality. The atmospheres cancel, the Pascal cancel, and we're left with kilopascal for the units. In the calculator, you do 0.892 times 1,103.25 and divide by 1,000. The calculator answer is 99.501, etc. We keep 3 sig figs. Remember how 1 kilopascal equals 1,000 pascals are exact numbers by definition. 1 atmosphere is exact. The pascals here, there is 6 sig figs. So that's the given amount who will limit to 3 sig figs. So we keep 99.5. What comes after is a 0. So we run down and we keep the 0.5 and drop everything after.